Hello, this is a video for EDX Statistics 1. This is the first video in this series and it will look at the Poisson probability distribution as a model. Many situations occur where we are interested in how many times some things happen within a set period of time or space. Here are a few examples. In such situations, we're often interested in whether the events occur randomly. So we need a probability distribution which can be used in these situations. The Poisson distribution is such a distribution. It takes its name from the French mathematician Simeon Poisson who first proposed it. The conditions of the Poisson distribution are that events must be independent of one another and must occur singly rather than in pairs or groups. The Poisson distribution allows us to calculate probabilities where we know the mean rate at which events occur. For example, if we knew the mean rate of births per hour in a hospital, we could calculate the probability of getting a particular number in any given hour. This is the formula for calculating Poisson probabilities. We are not going to cover the use of this formula during this video. That will be covered in the next one in this series. For now, I will just say that lambda is the mean rate at which events occur. You can see that the possible values that x can take are any positive integer, and we can write down that x is a discrete random variable from a Poisson distribution with a mean rate lambda like this. The only other symbol here is e, which is an irrational number like pi, which cannot be represented as a fraction, instead only as an infinite non-repeating decimal. You may have already met this in many other areas of mathematics. Here is the shape of the Poisson distribution. As you can see, the highest probabilities cluster around the mean, and whilst it might appear that there are values for x which have zero probability, in fact all of these values have a probability greater than zero, just very small, and it can't be shown on this diagram. You can see as I change the value of lambda, the shape of the distribution changes as well. Here are the conditions of the Poisson distribution, where x represents the number of occurrences per interval of time or space. The events must occur at random and also independently of each other, meaning the occurrence of one event doesn't have any impact on the occurrence of another one. When we say that the rate is proportional to the interval, we mean that, say we have 5 events on average in 1 hour, then we would have 10 events on average in 2 hours. And also, as already mentioned, we must have all events occurring singly rather than in pairs or groups. Here are some examples of scenarios that might be able to be modelled as a Poisson distribution. The number of phone calls on a randomly chosen day may be modelled by a Poisson distribution, but we need to ensure that those phone calls are independent of each other. So for example, if you received a phone call and then made a phone call as a result of it, those two things would not be independent. Similarly with insurance claims made by motorists in a given amount of time, if two motorists have crashed into each other and they both make a claim, then those two things would not be independent of each other. Particles emitted by a radioactive source would probably be random and independent of each other, but you may have a situation where the rate isn't constant, particularly where the amount of radioactive material is decreasing. The number of cars passing in a randomly chosen 10-minute period would require no traffic problems. So for example, traffic lights where you are having a disruption in the constant rate of flow, you would need for that not to be the case. Similarly, number of accidents in a factory per month, it's worth thinking about whether you think that those things would be random, independent, whether they're going to be at a constant rate, and it's depending on the factory and depending on the different scenario, that may or may not be the case. Similarly, with the number of typing errors on a randomly chosen page from a large document, it's possible that when you mistype one word, you then make another error soon after that because your fingers are in the wrong place. You might decide that you can't model that with a Poisson distribution because they're not independent of each other. That's the end of this video. The next video in this series is looking at the Poisson distribution and how to calculate probabilities.